Imagine we have a spring and we attach it to the ceiling. Let's see if I can spell ceiling correctly. Ceiling. Now this spring doesn't have any mass attached to the bottom of it, not yet at least. And this is the length of the spring when it's relaxed, so its natural length. And this is the length of the spring when we don't have any mass attached to it. But let's say we wanted to try an experiment. We wanted to see what happened to this spring as we added more and more mass to this spring. Now we know that the spring is going to increase in length as we add more and more mass to it. And as we add mass to this spring, we decide to plot it on the graph. And what we're plotting is how far the spring has extended downwards as we add a load to the spring. So as we add a force or a mass to the bottom of the spring. And as we add mass to the spring, we get a force pointing downwards and a counteracting force pulling the string upward. And this is the tensile force. Now these forces balance out, and because they balance, it means that the spring is stationary, so it doesn't accelerate downwards. So as we start adding mass to this spring at the bottom here, we plot how far the spring extends from this 0 point here, from the point at the bottom of the graph. So if we add a 0.1 kilogram mass, the force on the spring would roughly be 1 Newton. So we can mark this on our graph here, 1 Newton. And we find that our spring extends down by, say, 0.01 meters. And remember, the force due to gravity is equal to the mass of an object multiplied by the acceleration due to gravity. And I'm assuming here, just to make our calculation easy, I'm assuming that g is equal to 10 meters per second squared. But as we keep adding masses to the spring, we find that we have a linear relationship up to some point P. This means as we increase the force on this spring, the spring extends by an amount proportional to the force. So the force is proportional to the extension. Now this only happens up to some limit called the limit of proportionality. And the limit of proportionality is simply where the linear relationship breaks down. So this no longer applies. And we find here that when we add even a little bit of load, the spring extends quite a bit until at some point the spring fails. Now this doesn't have to be a spring. It could be any material that deforms elastically. And this means, so elastic deformation simply means that when this load is taken off, the spring, or whatever material we're stretching, goes back to its original length, which we can call d. But this proportional relationship here between the load and the extension is expressed in Hooke's law, which is the force is equal to the spring constant multiplied by the extension. And this formula here also applies when we're compressing the spring. So instead of pulling it down, Hooke's law applies when we're compressing the spring. So when we're applying a force in the opposite direction. And we can draw this as a graph like this. So this graph here is represented in this quadrant here. So we got the load on the y-axis and the extension on the x-axis, and this goes up to the limit of proportionality up here, P. This part of the graph is linear, but we also, if we're compressing the spring, we also have a linear relationship in this direction, and the force is negative because a force is a vector and it's pointing in the opposite direction. So this is the negative direction and that would be the positive direction, until we also hit some limit of proportionality where the spring or whatever material we're compressing doesn't go back to its original length when the force is removed. So if we have a look at Hooke's law quickly, it looks very similar to the equation of a straight line graph. So y equals mx plus b, where m is the gradient or the spring constant here, and b in this case is equal to 0 because the straight line is going through the center of the graph here, and the y-axis is equal to the force that we're applying to the spring. So we know the spring constant depends on the gradient of the graph, which is the difference in force divided by the difference in the extension or compression. So we can rearrange this formula to isolate the spring constant, which is the force divided by the extension. And the units of the spring constant is equal to newtons over meter, or newtons per meter. So let's try a couple of questions. An elastic cord has a length of 25 centimeters. When the cord is extended by applying a force at each end, the length of the cord becomes 40 centimeters when the force is 0.75 newtons. So our goal here is to calculate the force constant of the cord, or the spring constant. So let's draw out a diagram of what this question is asking us. So if we imagine this is the original length of the elastic cord with no mass at the bottom and no force applied to it, we get a length of 0.25 meters. When we apply a force, a tensor force, to both ends of the spring or the cord here, and the force is equal to 0.75 newtons, the cord has extended by 15 centimeters. Our goal is to use Hooke's law, which is the force applied to this cord is equal to the spring constant multiplied by the extension of the cord. And I forgot to mention earlier that Hooke's law only works up to the limit of proportionality. So it only works when the relationship between the extension and the force is linear. After the limit of proportionality, the way that the spring or the cord extends is unpredictable. So our extension is the difference between the lengths here. So d2 minus d1 is equal to our extension, which is equal to 0.40 meters minus 0.25 meters, which equals 0.15 meters. So we've got the extension up here. We have the force of 0.75 newtons, so that's the amount of force required to extend this cord here by 15 centimeters, 0.75 newtons. And what they're asking us is to find the spring constant here. In other words, the gradient of this graph. So we can just rearrange Hooke's law here. So the force divided by the extension is equal to the spring constant, which is equal to 0.75 newtons divided by 0.15 meters. And we get a value of 5 Newton meters, or newtons per meter. Okay, so the next question is a bit more tricky. We have a steel wire that extends by 1.5 millimeters when it's under a tensile force of 45 newtons. So we can already tell that a lot more force is required to extend this steel wire. So let's imagine we've got a mass on the end of the steel wire here, and that's its original length, and this is the length that it's extended by. So 1.5 millimeters, if we are to convert that to meters, that is 0.0015 meters, or 1.5 times 10 to the minus 3 meters, and a tensile force of 45 newtons is applied to this wire. 45 newtons. So it's saying here that the limit of proportionality has not been exceeded. So let's draw our graph so we fully understand what this means. So this is the load force on the y-axis, and on the x-axis is how much our steel wire has extended. Now, according to Hooke's law, the extension is proportional to the force up until the limit of proportionality, or P. So it's saying here that under these conditions, we're still in this region here. So the limit of proportionality is not exceeded. We haven't gone past this point. So let's say this is 1.5 millimeters, and we've achieved this with a force of 45 newtons. The question asks us, what is the tensile force required to produce an extension of 1.8 millimeters? So let's say 1.8 millimeters is here, further up the graph. So we already know that the force is going to be higher than 45 newtons, but we don't know what this force is yet. So what do we need to find out first in order to calculate this force? Well, what's missing is the spring constant. We don't yet know what the gradient of this graph is. So Hooke's law is force equals to the spring constant multiplied by the extension, and the spring constant is equal to the force over the extension. So we need to work out the spring constant first. We've got a force of 45 newtons, extends this steel wire by 1.5 millimeters. So our spring constant is equal to 45 newtons divided by 1.5 times 10 to the minus 3 meters. We get an answer of 30,000 newtons per meter, or 3.0 times 10 to the 4 newtons per meter. So this gives us the gradient of our graph here for Hooke's law. Now we can find out the tensile force required to produce an extension of 1.8 millimeters. And we can go back to this formula up here to isolate the force. So the force is equal to this spring constant here, 3.0 times 10 to the power of 4 newtons per meter, multiplied by the extension here, which is 1.8 times 10 to the minus 3 meters. And this gives us a final answer for the force of 54 newtons. 54 newtons.